So our problem is that with those given data, how do you calculate the performance matrices that are listed on this page? And we talk about that to get, for example, the first simplest performance measure, the flow time. We need to know that what's the value adding time, which are pretty clear. Those processing times, those are the value adding time. And also need to know the waiting time. But those waiting times, for example, the time that those work parts need to wait in the queue, need to wait in the petty log storage, those are not given. And they are dependent on all the other parts and their behaviors in the system. Plus, there's also waiting time on single machines um, simply because they don't have any buffers. If the machine next in the row is occupied, then the part will have to be wait at its current location before the next location is freed. So let me give you some hints how to calculate that. So we talk about that we need to really looking at let's start slow and looking at the first few items. For example, the first one item, when does it enter into the receiving dock? It's at 2.92 minutes. Okay, so this one is 2.92. Okay, and when it exits the receiving dock, since this is the first item in the system, it can exit right away. So it really equals to its enter time, and then it will enter into the splitter right away. And when does it complete? Would be the time it enters plus the time it takes to complete the work on this splitter, this value here. And then it can exit right away. So the exit time equals to the complete time, and then it will enter right away, exit right away, because this is a queue. It does not have any processing time on it. It just slips through the queue and goes to the next location. So these are all the same. And then when it at the lathe queue, the complete time will be its enter time plus its processing time in the lathe. So in the lathe, the processing time for the first item is this one. Oh, and the enter time plus. Okay, and then its exit time would be equals to the complete time. Enter to the next location equals to the exit time. The complete time equals to, again, the enter time plus the paint booth performance time. Paint booth performance time. And its exit time equals to be the complete time. Enter time equals to the exit time. Complete time equals to the enter time plus the processing time on the oven. The first one. Okay, and then its exit time equals to be the complete time here, and it will enter into the paint log storage. However, we'll need to be really careful about this exit time. I mentioned that the logs will need to wait until the first 9 logs need to wait until the 10th log finish and they enter together, because we have a control logic here that at this painted log storage, they need to collect 10 before shipping them out. So the calculation here, this exit time actually equals to be the 10th item's exit time, which we don't know yet. But I'm going just to put this formula here to make sure that when we have the value here, it's the same. Okay, and you will imagine that for the first 9 items, the formula is the same. So let's just fix the row number here, the 14. Fix this row number here and then copy it all the way to 9. just click into it to see. Yeah, it is. Okay. Then let's look at the second item. And just to make it easier for us to work and not going back and forth between these two sheets, because we know that we're going to use those data from the previous sheet. So let's copy the data from this sheet. Copy them to this calculation. Okay, so this is the receiving dogs and the splitter processing time. Paint booth, and the last one will be the oven. And while you're copying, I don't know how many of you noticed that there's a negative value here. This negative value is because it's generated from a normal distribution. If we go back to the data, here it's generated from normal distribution. And the normal distribution goes to infinity on both sides. So there's a possibility that we generate a negative value from normal distribution. And what we do in case of negative value happens, then is we change it to a 0. Okay, so here we're going to change it to a 0. Okay, I highlighted this representing that's the value that we changed. Okay, now we copy those values here to will be easier. So the first item is pretty unique because it's the first item into the system, and before that the system is completely empty. So it won't need to wait at any location. It can always go to the next locations because there's no item before it. But starting from the second item, we need to consider if the previous item finished their work there. And we can do so by observing the value difference between the first items and the second. But at this point, we want to put some formulas in our calculation so that it is as general as possible that we can maybe apply to other items done in a row. So here, second item. So the second item will arrive 1.56 minutes after the first item arrives. So will be the previous items arriving time plus its inter-arrival time that we just copied here. Okay, so this can be generated, this can be generalized for the rest of them, because when they enter into the receiving dog, you see receiving dog has a capacity of 20, and in total we only have 20 items. So that makes sure that all the 20 items can just get into the receiving dog when they arrive. So that means we can just copy this formula all the way down. Double click it, will be copied all the way down here, and just click into the last one to check. Okay, so the 20th item will come 1.14 minutes after the previous item. So the B25, yeah, okay, correct. Okay, so with this we finished the first the entering time for all the items. Okay, again, this is we can copy this formula here is because we have enough capacity to make sure all 20 items can just get into this receiving dock when as soon as they arrive. Now let's look at this exit time. If we think about the second item, when can it exit the receiving dock? It can't exit the receiving dock before it arrives, right? It has to arrive at the receiving dock first before it can exit. At the same time, it cannot exit unless the splitter is free, unless the splitter has a capacity for it to enter. So there are two numbers that we need to look at and compare. You see, the second item arrived at the receiving dock at 4.48 minutes. However, the splitter is occupied all the way to 5.17 minutes. So that means the second item has to wait at this receiving dock for about half minute before it can enter into the splitter when this first item exit. So how do we put a formula here? So this exiting time depends on the entering time. It cannot exit before it even enters into the receiving dock, and also cannot enter unless the first item finishes at the splitter and exit. So it is the maximum between its entering time and the exit time. And make sure you choose this exit time, not the complete time, okay? Because for some of the following items, the complete time and exit time will be different if their next location is blocked. They cannot exit as soon as they finish their work. Okay. So this formula, I think we can copy it all the way down because for the receiving dock, when it can exit depends on, especially the splitter only has like one capacity. So it's always comparing its entering time and the exiting time of the previous item. So we can copy it all the way down and click into the last one to see. Okay, so the 20th item cannot enter unless it arrived at its current location and the previous and the next location is free for it to enter. Okay, now moving here. The enter time is always equals to the exit time. This one is true for all of them. So double click and the formula will be copied. And we check it. Correct. Now the complete time is always the entering time plus its processing time. So for this one, we can double click again to copy it. So let's just check the last one. So it's the entering time plus its processing time. Okay, now the exit time. Again, based on the same logic as what we did earlier. Okay, this time one thing we need to pay attention is that the lace queue has a capacity of 8. What does that mean? Does this exit time of the second item based on when it's complete and also when the next when the previous item leaves the lace queue? Is this right? Think about it. Okay, first we want to make sure that the item does not leave the splitter unless it finishes its job. Okay, it has to be processed first. So it has to be the time it exits the splitter need to be after it complete the job there. But it also need to depend on whether it can enter into the next location. If you look at the next location, is it this value that we use? If we use this value, what does that mean? If we use this value, that indicates that the second item cannot enter into the lace queue unless the first item leaves the lace queue. So it's kind of like the second item needs the spot that the first item is in to get to the lace queue. However, that's not right because lace queue has a capacity of 8. So it basically can just enter into the lace queue because there's only one item here, right? The previous item, the item 1 only occupied the first unit of that 8 capacity. this second item can actually occupy the second unit of that capacity. So it does not really have to wait until the previous item leaves. So this second item can safely enter into the lace queue as long as it completes its work at the splitter. So this one equals to this. Okay. Then, can we copy this all the way down here? Probably not, because at a certain point, we need to wait. What happens if the lace queue is full? If the system is really blocked, the lace queue, all 8 capacity spots of this lace queue are occupied. Then the item in the splitter will have to wait. But when will that happen? Or until when we can safely copy this formula here? For example, the first one, the second one, third one, all the way to the 8th one, we can probably safely copy them, right? Because the lace queue has a capacity of 8. So we can copy the item's exit time. So until up to this 8th item, they can just exit the splitter and go to the lace queue, because the system starts empty and the lace queue has 8 capacity, so all 8 can just go there. What about starting from the 9th? Can it enter? Maybe or maybe not. So how do you think about this part? Okay, to think about that problem, let's do some drawing. Okay, consider this is the lace queue. Okay, it has 8 spots. 1, 2, 3, 4, 5, 6, 7, 8. 8 spots representing its 8 capacity. Okay, and then we have things, say if they are all occupied at a certain time. Okay, so they are all occupied, representing, for example, if this is the first one, okay, this is item number 1, and item number 2, 3, 4, 5, 6, 7, 8. If they are all occupied, then when can the 9th item enter into this queue? When the first one moves out, right? If we have the same, okay, the same queue here, okay? This 9th one can move in this queue when they all shift, well, the items all shift one location in this queue here. So now 1 is out, 1 is at the lace. Then that's the time when the 9th item can get into the queue. Okay, in the system, it may not be that all the first 8 items may not occupy the queue at the same time, but this is just for the safest, this is like the worst scenario. Let's say this will be the worst scenario. And if we get the worst scenario considered, then it can be generalized to cover all the different situations. Okay, so we know that the ninth item can enter when the first item exits the queue. That would be the same for the 10th. The 10th item can enter when this item 2 exits the queue, and so on. So with that, it will be clear that what formulas, hopefully it will be clear what formula we enter here. Okay, so the ninth item cannot exit the system unless it finishes its job at this splitter, and also the first item exits the queue. Okay, so you can see that this formula, when we copy it down, it always go back 8 items and compare. For example, here, let's copy, say the 12th item. So the 12th item would compare, say, okay, well, I have to finish my work first and then check if I have a spot in the last queue. And whether it has a spot in the last queue, it come back 8 spots. So from the 12th to the 8th. So if the 8th item already left the last queue, then I am guaranteed to have a spot in this last queue here. Okay, so now that's the formula for the splitter. Now at the last queue, the enter time always equals to the exit time. So that's a formula that we can safely copy. Because once they exit, especially we put all the locations next to each other. So when it exit the previous location, it enter the next location. So this can always be safely copied. And then when it can exit the last queue, then depends on the exiting time of the previous item at the next location. You can see here why we don't put a wait time. The wait time will be equals to the wait time between will be equals to the difference between the enter time and exit time, and those time is dependent. Okay, so it equals to be the exit time equals to be a maximum between its enter time. It cannot exit before it enters, and also it cannot enter before the next location is available, which depends on whether the previous item at the next location leaves that location. So maximum between these locations. You can see this one is it's the same. Okay, we're going to copy this formula here. These are all same because we have zeros here. Later when we get all the values in, then we will see there may be difference between here representing they are waiting in this last queue. So the wait time can be calculated by taking the difference between these two columns. Okay, the enter time equals to be the exit time. The complete time equals to be the enter time plus the processing time is the second item. Okay, so the enter time and then complete time. So let's check our formulas. Okay, correct. So it's the entering time plus processing time. Okay. And then the exit time will be maximum between this value here and the exit time of the painted booth. And so on. Okay, so I'll stop here and let you finish this entire spreadsheet. And then you can think about and calculate anything here that you can calculate from this calculation sheet. Okay, some of those performance matrices like the utilization, we can calculate from here yet. This has to do something we mentioned in the class that certain response variables like utilizations, you have to use the state variables to calculate. So if you finish this page, then I encourage you to think about how do you get those state variables. Namely, if a system, if a certain location is occupied at certain minutes. So for example, if you want to calculate the utilization of the receiving dock, which is a multi-capacity location, you really need to think about how many units are occupied at how many, for how many minutes. Or take this splitter, which is simpler. It's a it's a single capacity location. Then how do you get those state variables? You probably need to list down all the 96 minutes. Okay, list all the 96 minutes and say, okay, minute 1, is the splitter occupied or not? Minute 2, is it occupied or not? Get all those 0, 1 values. So create a new spreadsheet, get those 0, 1 values, and count how many ones are there. Then that gives you how many minutes out of this 96 minutes that specific location is occupied.